Pre-calculus, section 2.3, polynomial functions and their graphs. Today's objectives: identify polynomial functions, recognize characteristics of graphs of polynomial functions, determine end behavior, use factoring to find zeros of polynomial functions, identify zeros and their multiplicities, use the intermediate value theorem, understand the relationship between degrees and turning points, graph polynomial functions. So the definition of a polynomial function would be this, where we let n be a non-negative integer. A sub n minus 1 all the way through a1 are just real numbers. And a sub n is not equal to 0. If it were equal to 0, sorry about that, then this term would just disappear, and then we'd have a different a sub n. All right, but since it's not equal to 0, we do have this. So the number a sub n is the coefficient of the variable with the highest power, so the x to the highest power, and this is called the leading coefficients. All right, so there is the leading coefficient test. So as x increases or decreases without bound, i.e. as it goes to positive or negative infinity, the graph of the polynomial function, which we saw earlier, so here is the highest power, the second highest power, the lowest power. Here we actually have x to the 0th power, but that's just 1. All right, eventually rises and falls in particular ways. So we're looking for the n. We're looking for the power of our n, our leading term here, which in this case is this a sub n x to the n. If that n is odd, like a 1, 3, 5, 7, etc., then we can look at this chart right here. So if n is odd, if the leading coefficient is positive, the graph falls to the left and rises to the right. So something we recognize here is a line. With lines, our power of n is 1. 1 is odd. And if your slope is positive, then our line goes in ways like this. Whereas if your slope is negative, which is the next one, we have a line which looks something similar to this. So that's why we have these different end behaviors. As it goes to negative infinity, this is going to be moving downwards. As we're moving to positive infinity, this will be moving upwards for odd n and a positive coefficient. All right, and then likewise for a odd n and a negative leading coefficient, we're going to be going upwards as we go to negative infinity, and we're going to be going downwards as we go to positive infinity. What happens in the middle, that'll be different, but for now, we know what happens at the far, far ends of the graph. If our n is even, so that's 2, 4, 6, 8, well, we can kind of think of this like a parabola. Parabolas have a highest power of x of 2. 2 is even. Parabolas, if your leading coefficient, your a, which we saw earlier, is positive, then we have a parabola which goes upwards like this, which is one way to think about the end behavior for even, odd, and positive coefficient. Like I said earlier, what happens in the middle might change, but we know the ends will be doing this. So we can think of our even ends, our even powers of x that are the highest. We can think of their ends as how they work with parabolas. Likewise, if we had a parabola with a leading coefficient that was negative, we'd have a downward facing parabola. So that's why we have right here the arrows pointing downwards. Something's happening in the middle, but at the ends, they're going to be pointing downwards forever. All right, so now we're going to be using the leading coefficient test. So use the leading coefficient test to determine the end behavior of the graph. There should be a period there. All right, so here's where we have to be careful. Our leading coefficient is not this right here. It is, well, it's the coefficient, so it's this number right here. So it has the highest power of n. In this case, our n is equal to 4, which is even. So right away that tells me that we're going to either get an up, up, or a down, down. So now it's just a matter of determining whether our a is positive. Well, when we don't write a number, we know it's a 1. Since there's a plus sign, it's a positive 1. So we get our a is equal to 1, which is greater than 0. So we know that this is our answer. The downwards aren't actually there because, in this case, since it's even, we can think of a parabola. Something's going to happen in the middle. Actually, it's going to look something similar to this because we will eventually know that a fourth power points upwards like this or downwards, and then it looks like a W. But yeah, so there's your n behaviors. All right. Same kind of thing here. We're going to be using the leading coefficient test to determine the n behavior of the graph of this. So here, everything is in factored form. So it's just a matter of determining what our power is going to be. We could say this is a 3x squared times x cubed plus 2 times x cubed plus 2 times x minus 1. And we can distribute all of that stuff. Not going to waste my time. I know for a fact that when I multiply this times this, I'm going to get a 3x to the 5th. And that'll be the highest power of x from that first thing right there. I know when I multiply this times this, I'm going to be getting an x to the 4th, which will be the highest power of x from doing that one. And then if I did all the multiplication, I'd be getting a whole bunch of terms here. We'd have to be combining stuff. But here, I know that those will be the highest powers from just doing those two multiplications. And since they're still being multiplied, I need to multiply those together. I'm going to get a 3x to the 9th. There's a whole bunch of other terms. We could use Pascal's triangle. We can do all kinds of stuff. Use our binomial theorem. All in all, well, I can't use binomial theorem. Wait, we could. All in all, we're going to be getting our highest power being odd. So here, n is equal to 9. That is odd. Our a is equal to 3, which is greater than 0, so that's positive. So we're going to be getting something similar to the line. Our n behavior, and I should have done an ordered pair on the last one, is going to be down to the left and up to the right. It'll have the same n behavior as a line. All right. If you don't like what I did there, feel free to multiply all that stuff out there. But I'm trying to show you some shortcuts so that way you don't waste a bunch of time on quizzes and tests doing more math than you have to when you're just looking at the highest power of x. And I know for a fact that this and this, doing that multiplication, will be my highest power of x. Doing this times this will give me those multiplications' highest power of x. Then it's just a matter of combining those highest powers of x together. Whenever I select the yellow highlighter, I always pick something else. Then I have to combine those together to get the highest power of x. Okay, halfway there. Slide 7 of 14. We need to find the zeros of a polynomial function. So here we need to factor. We may or may not have done much factoring like this in the past. I encourage you all to look at my factoring strategies handout, which I posted in Google Classroom. But here, I'm going to factor by grouping. We have 4 terms. When we have 4 terms, we always try to factor by grouping. So I'm going to group x cubed plus 3x squared. I'm going to put a plus sign in the middle of them. Then I'm going to group negative, I want to do black there, negative 2x minus 6. And here we're looking for greatest common factors. For this first group, I can see that there is a greatest common factor of an x squared. They both share x's. X squared is the lower of the two, so that's going to be our greatest common factor. So we can factor out an x squared, be left with an x plus 3. For the second set, there's no x's. They're both negative, so we can factor out a negative for sure. And they're both even, so we can factor out a 2. So I'm going to factor out a negative 2. If I divide the first term by negative 2, I just get an x, positive x. If I divide the second term by negative 2, I get a plus 3. Now we have one more step for factoring by grouping. Now we need to realize here that they both share a common factor of this x plus 3. So we can factor that out and get an x plus 3 times x squared minus 2. And then we have to factor again. Here, we are going to have x squared minus 2, which, let me just show this to you on the side here. If I do the square root of 2 times the square root of 2, that equals to be just 2. So what I can say here is that the square root of 2 squared is equal to 2. So what I can say here is we have an a squared minus b squared, which we know is just, I have to write below it because I ran out of space, so I'll just move it off to the side. That this is an a minus b times an a plus a b. We have the difference of squares. So we can get our x plus 3. Our a is x, and our b is the square root of 2. Our a is x, I wrote a, and then our b is the square root of 2. So there is the whole thing factored. If we set each of these equal to 0 because of the zero product property of multiplication, we could realize that here we get x is equal to negative 3, x is equal to square root of 2, and x is equal to negative square root of 2. Or it's just one answer, x is equal to negative 3, comma, negative square root of 2, comma, square root of 2. And that is our answer. All right, same thing, finding polynomials, finding zeros of a polynomial. So we're going to factor again. We're going to get, and what I didn't do is I should have said that this is all just equal to 0. Bad on me, because if they're zeros, that means our y is equal to 0. Our zeros are our x-intercepts, where our y is equal to 0. All right, so here we're going to say that 0 is equal to x cubed minus 5x squared plus 6x. Here we have 3 terms, but they all share an x in common, so we should factor out our greatest common factor of x. So 0 is equal to x times x squared minus 5x plus 6. And now we need to see, okay, do we have any multiples of 6 that add to become a negative 5? All right, so things that multiply to make 6 that add to become negative 5. Well, 1 times 6 gives me 6, but when I add them together, I get a 7. 2 and 3 add to become, or multiply to make a 6. They add to become a 5, but they need to be both negative, so that way they add to become a negative 5. So here we get x times x minus 2 times x minus 3. So for now, this is kind of a shortcut. I didn't do all the steps in the middle. If we get a more complicated problem, I will be sure to do those, but you do have that factoring strategies worksheet, which I already mentioned once. Okay, moving on. So now we just set all these equal to 0. We get x equals 0. Easy. x equals 2 and x equals 3, or x is equal to 0, 2, and 3. Factoring, it's your friend. All right, so now we have multiplicity and x-intercepts. So for now, I'm going to go backwards. I think I had an example up here. Where was it? Here it was. So this was in factored form. Let me go ahead. There we go. So with this problem, which I'm going to go ahead and write down and copy, f of x equals negative 3x squared times x cubed plus 2 times. I'll just stop reading and just write. Okay. Gonna copy that. Gonna go back to where we're actually at so that way I can use an example here. Okay. So multiplicity and x-intercepts. If r is a 0 of an even multiplicity, then the graph touches the x-axis and turns around at r. So in this case, here's what I'm looking at. I'm looking at this 2. Right here we have a multiplicity of r is equal to 2. So where that 0 happens, we're going to hit the x-axis and turn around. So that's going to happen, let's see, a negative cubed root of something. So that's going to be less than 1. So we're going to get something which kind of touches and turns around, maybe like this. All right. If r is of an odd multiplicity, so in that case, that's like this one over here, because it's x minus 1 to the first power. So in this case, it's going to cross through the x-axis. So in this case, I didn't do a very good job of drawing this because I wasn't thinking that far ahead. We're going to kind of touch and turn around and then kind of cross right through. Let's see if I can do that again. One of these days I'll get it. There we go. We'll say that's it. And then we'll continue on with the blue one to kind of cross through at that point. So Q... Oh, this would have been a negative 2. Oh, look at that. Okay. So here we kind of touch like this. We come back up, and then we're going to turn around and go through there. Okay. So this one would have been a negative 1 point something. And then this one would have been an x is equal to 1. So the horrible graph. Let's just move on. Okay. So regardless of whether the multiplicity of a 0 is even or odd, graphs tend to flatten out near the zeros with multiplicity greater than 1. Okay. So what they're trying to say here is that if I were to look at this 0, that pink one I have right there, it kind of flattens out near the 0, which, yeah, it turns around because it has a multiplicity greater than 1. The blue one, which actually had a multiplicity of 1, goes right through. It doesn't flatten out at all. But if we had like a 0, which was to the 3rd or 15th power, it would kind of flatten a bit. It wouldn't go straight through the line. All right, moving on. Here we go. We've got an example. We got nice numbers here. So find all the zeros and their multiplicities. Find the zeros of f of x is equal to 5 times the quantity of x minus 1 squared times the quantity of 2x plus 5 cubed. Give the multiplicity of each 0. State whether the graph crosses through the x-axis or touches the x-axis and turns around at 0. All right, so we have f of x is equal to 5x minus 1 squared times 2x plus 5 cubed. I'm going to ignore the 5 because it doesn't matter. 5 is just a number. We're not going to get any zeros. We need x's. So here, this one gives us x is equal to 1. It has a multiplicity, which I'm going to make m equal to 2. So here it's going to touch and turn around. This one, on the other hand, I'm going to actually do the work here because it's multi-step. We have a 2x plus 5 equals 0, subtract 5. 2x equals negative 5, or x is equal to negative 5 over 2. With that one, because of the power of 3, we have a multiplicity which equals 3. So here we're going to cross the x-axis because it's odd. Even, we touch and turn around. Odd, we cross. All right, 7 examples. Here we go. Maybe we'll start doing something hard soon. Who knows? Okay, the intermediate value theorem for polynomial functions. Long title. It's not that bad, though. Let f be a polynomial function with real coefficients, so no imaginary numbers, if f and a and f of b have opposite sign. So if f of a is positive and f of b is negative, or vice versa, then there is at least one value of c between f of a and f of b for which f of c is equal to 0. Equivalently, if f of x is equal to 0 at least one root between, or yes, okay. So what this means is, let's just make a graph. If here I've got A, here I've got B, and then here I'm going to have my f of A, and then here I have my f of B. So then I'm going to get a dot here and then a dot here. What this says is if I know these two numbers, then there has to be a 0 somewhere in between. There's no magical way that we could go from this value up here to this value down here without somehow crossing through the x-axis. It's just impossible. And the opposite is true. If, on the other hand, we had, let's see if I can save myself some time. Copy, paste, and then I'll just change that to B and A. So if we had some sort of f of b up here and then some sort of f of a down there, there has to be some way that we have to cross through that x-axis to get to those things. That's all the intermediate value theorem is saying, is there is some value at c. By the way, that's c, that you have to cross through the x-axis. We're going to use it. Show that the polynomial function of f of x is equal to x cubed plus x minus 11 has a real 0 between 2 and 3. Folks, take out your calculator. It's really just that. Okay, so first we have to do our f of 2, which is equal to a 2 to the third plus 2 minus 11. Let's make that 2 a little bit nicer. And that's a minus 11, not equals 11. And let's see what that equals. So we get 2 to the third plus 2 minus 11, and I get negative 1. Okay, so that is greater than 0. F of 3, on the other hand, we need to do a 3 to the third plus 3 minus 11. So what do we get here? I get this is equal, oh, sorry, that was less than 0. So I get a 27, which is greater than 0. So here we see that there has to be a 0 between the numbers 2 and 3. What it is, I don't care. We just showed that there is one. Holy goodness. Okay. Let me turn my face off here. Okay, so function f of x is equal to all that good stuff. Here's our process for graphing this. Step 1. Use the leading coefficient test to determine the graph's end behavior. Okay. Do we get something along the lines of a down up and up down, a down down, or an up up? So that right there, we can graph the end of the graph just right then. Find x-intercepts by setting f of x is equal to 0. That's our factoring we did earlier. if there's an x-intercept at r as a result of x minus r equals k, then use your multiplicity. So if it's even, it touches and turns around. If it's odd, it crosses through. If k equals 1, then if it's greater than 1, if k, the power, is greater than 1, then the graph just flattens out at that point. Use symmetry. So we'd gone over symmetry before. That was back in chapter 1, where we replace all of our x's with negative x. And if we get the opposite, or if we just see that all of our powers are odd, then we have y-axis symmetry, or symmetry. If I think I got those backwards. Okay. If our origin symmetry, so if we plug in that, we get all positives, then we have origin symmetry. Yeah, those are backwards. All right. This one should be negative, and then the other one shouldn't. Oh, I wanted that. The other one should just be positive. So if it's even, you have y-axis symmetry. If it's odd, you have origin symmetry. Okay, cool. Fixed it. And then use the fact that the maximum number of turning points of a graph of n minus 1 is where n degrees of the polynomial function. Okay, so if we have a polynomial function where we have f of x is equal to x to the 5th, this means that we're going to have 4 turn around points. I'm going to quickly give us an example where we had the f of x was the highest power was the 4th power, and I had said that we had a graph which looked something like this. Well, here we had 1, 2, 3 turnaround points. We had 1 less turnaround point than we had highest power of x. So it's good information. All right, let's do our last example, call it a day. Okay, we're going to graph this polynomial function. So first off, we're going to do our n behavior. So our n is equal to 5, that's odd. Our a is equal to 1, that's greater than 0. So we're going to have an n behavior of a down and an up. So if I were to go ahead and start my graph, I could go ahead and say, well, we know it's going to look something like this. Okay. Over here, we're going to be pointing downwards forever. Here, we're going to be pointing upwards forever. What happens in the middle? Who knows? We have to find out. Okay, let's do this. Let's see. How can we factor this? Well, we can take an x out of everything. So let's start that up here. We're going to get 0 is equal to x times x to the 4th minus 6x squared minus 7. Oh, now what do we do? Well, here's a trick. When your middle term is exactly half of your highest power, we can use something called u substitution. And I highly suggest you use u substitution because it's a topic in calculus. So I'm going to say let u equal x squared. So then we're going to get, I'm going to leave this x here because we haven't done anything there yet. So we're going to get a u squared minus 6u minus 7. So now that looks like something that we can graph, we can factor. Using our little thing, we're going to get a negative 7. That I cannot write. And then it adds up to be a negative 6. 7's a prime number, so it only has 1 and 6. We're going to have a 1 and a 6. Sorry, 1 and a 7. We want a negative 7 and a negative 6, so we need to have this 7 be negative. So we're going to get an x and then u minus 7, u plus 1. And then since we know that u is equal to x squared, we're going to get an x squared minus 7 times an x squared plus 1. All right, I'm going to use a slightly different method here. Instead of factoring it again, I'm going to say let's x squared minus 7 equals 0. So x squared is equal to 7. So then our x has to be equal to plus or minus square root of 7. We'll find that out shortly. And then for the other one, we're going to get x squared plus 1 is equal to 0. X squared is equal to negative 1. Imaginary numbers, not even bothering. So here we only get this and 0. So let's go ahead and graph those. We have 0. What is the square root of 7? Well, let's ask our calculator. So that's going to be plus or minus, we'll just say 2.6. We don't need the actual value, we just need something approximate. So here we're going to say 2.6, let's see, 1, 2, and we'll say that's about 6. 1, 2, that's about 6. All right. Now, each of these have a multiplicity of 1, so what that means is we're going to be crossing through each time. So I say multiplicity of 1 because we have a power of 1 here and a power of 1 there. So here we go. Let's cross through. Let's use blue. We're going to take this. We have to cross. We're going to turn around. We're going to cross. We're going to turn around and go all the way through. Okay. So yes, that one thing I just said right up here, use the fact that the maximum number of turning points of a graph is n minus 1. It doesn't mean that it has exactly that many. That just means that that's the maximum amount. So since our highest power here is a 5, we're going to have up to 4 turnaround points. But since 2 of those came from an imaginary number, we only have 3. And there's our graph. All right, folks. 32 minutes of video. We can stop there.